Hello, this lecture is going to cover the first half of chapter 4, where we start talking about molecules and what kind of bonding they have. So we're going to talk about ionic and covalent bonds. Okay, so this is chapter 4, and the outline is we're going to talk about ionic bonds, covalent bonds. We're going to talk a little bit about how you name chemical or how you name structures, so how you name molecules. Then we're going to talk about Lewis symbols and structures, which is a very simple way to talk about and describe the bonding within molecules. And we're going to talk about formal charges and resonance. That's part of Lewis structures, and molecular structure and polarity. So the first little way they get you interested in thinking about how bonds form and what they mean about structure is talking about buckyballs, a molecule that was discovered not too long ago, which is a carbon structure, and carbon has lots of different structures. So carbon as a solid can form diamond and it can form graphite, but in not too long ago, they also discovered it could form these structures, which are called buckyballs. And so we'll look at what it means to have these lines and double lines and what that means about geometry as we go through this chapter. So ionic bonding, once you form cations and anions, which we've already talked about, then you can form ionic compounds. So we can predict the charge of common metallic and non-metallic elements and write their electron configurations. And that will help us understand some of the trends in the periodic table, like why the halogens like to be -1. So these are just some pictures to show you that when you form an ionic compound, A is a sample of sodium, neutral sodium metal, and it's a soft metal. And here it's shown covered with mineral oil because it's a super reactive metal. And then in B, you see a sample of chlorine gas. So chlorine is a diatomic molecule at room temperature, and it forms this yellowish gas. And when those two react together to form sodium chloride, you get this crystalline salt. So sodium metal, chlorine gas, they're both very reactive, and chlorine is really toxic. But when you get sodium chloride, very different properties, and it's something that we need in our diet. So this just shows you that when you're talking about ionic compounds, you don't have single bonds. You don't have just a sodium bonded to a chlorine, doesn't show the structure. You have this massive structure where there's every cation is bonded to several anions, so it depends on the structure. For sodium chloride, it's this very symmetric structure, so that each cation is bonded to 6 anions, 1 on each side. And then chlorine is the same way. It's bonded to 6 sodium cations. And so you have this structure where all of those bonds together hold that sodium chloride in the solid phase. So covalent bonding, we have talked about this a little bit. It's when molecules are formed by the sharing of electrons rather than by one picking up electrons and becoming an anion and the other losing electrons and becoming a cation. So this is a different type of bonding. We're going to define something called electronegativity, and that will help us think about why some covalently bonded molecules are polar. This is just a picture that represents why a molecule would form and have a covalent bond. So on the x-axis is the distance between 2 hydrogen atoms, and we're going to think about why H2, the molecule, forms. On the y-axis is the potential energy. So if you have 2 separate hydrogen atoms, because their distance is too long to be a molecule, then you have a certain energy. As they get closer and closer together, this picture shows you that their energy goes down. And at the very lowest point in that picture, that would be the energy of the stable distance for an H2 molecule. So that just shows you that molecules form covalent bonds because it lowers the energy of the system. This is a picture of HCl. So HCl also forms a bond in the similar way, and you could think of it as the same picture, except one would be an H and one would be a Cl, chlorine. But this arrow above the molecule is representing the fact that chlorine is more electronegative. And so when it's sharing electrons with hydrogen, it will pull more of the electron density towards the chlorine, making that end of the molecule a little bit negative. So that's what that arrow represents. You're leaving behind a little bit of positive on the hydrogen, and the arrow represents which way electrons are being pulled. In B, it's just another way to show that same picture. The delta, lowercase delta, means it's a little bit positive on the left-hand side and a little bit negative. You haven't completely pulled an electron off, but you have pulled some of the electrons towards the chlorine. And so this gives you what the trend in electronegativity is. So electronegativity is the ability to pull electrons towards yourself when you're sharing electrons in a covalent bond. So with hydrogen and chlorine, chlorine is more electronegative than hydrogen. So more of the electron density is pulled towards chlorine. This shows you that the most electronegative element is fluorine. And as you go back to the left, it goes down in electronegativity. And then as you go down a group, it goes down in electronegativity. So the very most electronegative element is fluorine, is the best thing to remember. And any way you go away from fluorine, things go down in electronegativity. So Linus Pauling created this electronegativity scale. And they talk a lot about him in your book. He is the only person to ever get 2 Nobel Prizes completely by himself. So single awards to him. One was for chemistry and one was for the Nobel Peace Prize for his work in trying to fight nuclear weapon production. So this talks about whether or not we would call a molecule ionic, covalent, polar covalent. So when you have a difference in electronegativity that's less than 0.4, then you're going to call it pure covalent, where they're sharing pretty equally and it won't be a very polar molecule. But if it's between 0.4 and 1.8, and these are units of Debye, which I'm not sure your book even gives those units, but that's what the units of electronegativity are. And so if it's in that range, we call it polar covalent. You haven't completely given up an electron or picked up an electron. You haven't created ions, but they're not sharing equally, the 2 atoms. And so one end of the molecule will have a slightly positive and the other slightly negative charge. If the difference in electronegativity between the 2 atoms that are bonded together is greater than 1.8, then we say it's ionic. Pretty much an electron has moved from one atom to the other. So once we look at these structures, now we have to have a way to name them. So we're going to derive names for common types of inorganic compounds using a systematic approach. So that's what you'll find in chemistry. There are rules for all sorts of things, but definitely for naming things so that we're all on the same page. We'll have rules for how we name things. So nomenclature is a collection of rules for naming things. Compounds are identified by both their formula and name. So you could write the formula for something, or you could give the name, and both of those should give you all the information you need. So we'll learn how to name the following types of inorganic compounds. The first will be ionic and molecular binary compounds, so composed of 2 elements, and then ionic compounds containing polyatomic ions and acids. So first, if you have an ionic compound, you're going to name the cation first, followed by the name of the anion. So a monatomic cation is just given the name of the element, and a monatomic anion is given the name of the element with its ending replaced by the suffix ide, IDE. So a polyatomic ion is just given the name of the ion. So we'll see those. We already saw a table of those. So to make sense out of that, sodium is the cation, chlorine is the anion. So it's going to be sodium chloride, potassium bromide, calcium iodide, cesium fluoride, and so on and so on. So if you have a polyatomic ion, you go to that table that was in chapter 3. I don't think they give it again here, where each of the polyatomic ions has a name, so you don't have to memorize them. But for example, on the top of the right-hand column, calcium is just the element. It's a monatomic cation, but sulfate is SO4 2-, and so it's called calcium sulfate. So I would have gotten that sulfate out of the polyatomic cation and anion table. So each of these, so the same naming, potassium acetate, potassium is K+, the C2H3O2 is the acetate polyatomic ion, ammonium chloride, ammonium is a polyatomic cation, NH4+, and then the anion is chloride. So if you want to name ionic compounds containing a metal ion with variable charge, so when we look at the periodic table, especially in the transition metals, oftentimes they can have more than one charge as a cation. And so because of that, you have to give that information somehow in the name. So the charge of the metal ion is specified by a Roman numeral in parentheses after the name of the metal. So iron can either be +2 or +3. So if it's FeCl2, that gives me the information that if I have 2 chlorides and each chloride is -1, that means that the iron has to have its +2 charge. And so in order to represent that on the right, it shows you, I would call it iron, and then in parentheses, the Roman numeral 2. So it'd be iron 2 chloride. So when you have the next one where you have 3 chlorines for every iron, then we know that the iron is in its +3 charge state. So it's going to be an iron 3 chloride. And same as you go down in each of these, you can look at anything that has more than one possible charge. You have to give that information. So when you looked back at these guys, or this one's better, sodium chloride, sodium's always +1, chlorine's always -1, potassium's always +1, bromine's always -2, calcium's always +2, iodine's -1. So you can see in this case, you don't have to give information about what charge is on the ion because it's always the same. So when you're naming a hydrate, it's a pretty trivial addition. So a hydrate is just a molecule that picks up water, which is pretty common. So if you have something like copper sulfate, the first formula given here, and it's has 5 waters attached to it, then you'll call it copper 2 sulfate, because that's what that name is, because copper can be +1 or +2. But in this case, because sulfur is -2, I know it's the copper 2 sulfate. And then I say how many waters are on it. So pentahydrate has 5 waters, whereas calcium chloride only has 1 water. So it's calcium chloride monohydrate. And these are those prefixes. So I'd also give you this: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca are all the prefixes for the number of water molecules, or in just a second, the number of atoms when we go through another nomenclature system. This is another highlight that they have in your textbook about Erin Brockovich, and she has a very, very interesting story. I can't remember. Oh, gosh. I can't remember the movie that's made about her, but it's older. But she filed a lawsuit and actually won for the chromium that a company was putting into the water that was making people sick in her neighborhood. So she's a good person to look up if you're interested. So another nomenclature system is naming binary molecular compounds. So far we've named things that are bonded ionically, but now we're going to name things that are bonded covalently. So we have a different set of rules because these are covalently bonded molecules. Covalently bonding allows for significant variation in the ratio of atoms in a molecule. So we'll see that you have carbon monoxide, carbon dioxide, and they just have a different carbon to oxygen ratio, but that's very, very common for things that are covalently bonded. So the names for molecular compounds must explicitly identify these ratios. Makes sense. The name of the more metallic element, the one further to the left and or at the bottom of the periodic table, is always named first, followed by the name of the more non-metallic, the one further to the right or at the top. And the second one, the less or non-metallic one, has its ending changed to the suffix "ide." So the number of atoms of each element are designated by those Greek prefixes that we gave right here. So when only one atom of the first element is present, the prefix mono is usually not used. And when two vowels are adjacent, the A and the Greek prefix is usually dropped. So we'll look at some examples of that. So if you have one sulfur and two oxygens, you're not going to call it monosulfur dioxide, you'll just call it sulfur dioxide. And then sulfur trioxide, nitrogen dioxide. But now when you get to N2O4, you do have to specify that it isn't mono. So you say it's dinitrogen tetroxide. So you leave off the A, like they said, you leave off the vowel. So yes, you leave off the A in the prefix. So rather than saying tetraoxide, it's tetroxide. So then same thing with dinitrogen pentoxide instead of pentaoxide. So you can look at each of those. So you're just using those prefixes and the names of each element. The second one changed its ending to IDE. So we're going to skip the part on naming acids. When you take Chem 108, if you do, you'll do chapter, probably, I think it's 3 chapters in that course, which is about an 8-chapter total course. So a significant part of the course is on acids and bases. And we're not going to spend that much time talking about acids and bases. So I don't think we'll go into the very detailed nomenclature for acids. So are the oxyacids. Okay, so here's where we'll pick up in our second lecture. So we've talked about ionic and covalent bonds, looked at some of their structures and how you name them. And now we'll go through a very simple model called the Lewis model of how to represent bonds and shapes of molecules. We'll do that in a second lecture.